Assalamu alaikum, my dear students. I hope all of you are fine and doing well. So, in our today's lesson, we will discuss the demonstration of the Gram's law, that how we can verify this law. So, the simple method for the verification of the Gram's law, we can do it in the laboratory by taking the simple examples of this. So when we are going to do it in the laboratory, so first of all we have to look what was the Graham's law of diffusion. It was basically the relationship between the rate of diffusion of the gases and the simple their density. So the rate of diffusion is inversely proportional to the density of the gases. So for this verification we have to take a long glass tube in which we will insert the two cotton plugs. One was soaked in HCl solution and the other was soaked in the simple ammonia, or we can also soak it in the ammonium hydroxide. So at the end, we just have a look on the distance traveled by the both gases, which is HCl and the ammonium hydroxide. So we just notice that the HCl covered the distance of 40.5 centimeter and the ammonia covered the distance of 59.5 centimeter. So the equation that we just have there, ammonia reacts with the HCl and it produces ammonium chloride, as ammonium chloride are produced in the form of white dense fumes, and it produces the white dense fume at the point of junction. So we just notice the production of these white fumes and we just calculate the distance traveled by these two gases. So the equation for this calculation we have, it is the rate of diffusion of ammonia divided by the rate of if diffusion of HCl, which is equal to the square root of molar mass of HCl to the square root of molar mass of ammonia, as the rate of diffusion of ammonia is 59.5 centimeter, and divided by the rate of diffusion of HCl we have, it is 40.5 is equal to, next we have the molar mass of HCl. So HCl is equal to 1 plus 35.5, it is 36.5 gram per mole. So this is the molar mass of HCl, we have 36.5 divided by molar mass of ammonia. So NH3, in which ammonia is nitrogen having 14 mass number and hydrogen is 1, multiply by 3, we have 17 gram per mole. So the square root of 17, or the molar mass of the ammonia. The answer we gain, it is 1.46, which is equal to 1.46. Hence the law is verified by this simple example. The rate of diffusion of two gases and the ratio of the square root of the molar mass of two gases is equal to each other. Next, let's have an example for the calculation of simple rate of diffusion. So we have 250 centimeter cube of sample of hydrogen that diffuses 4 times as rapidly as 250 centimeter cube of an unknown gas. Now we have to calculate the molar mass of that unknown gas. For this purpose, we have to just let the simple thing, let's we have an unknown gas, and this unknown gas can be represented as X or with the symbol X, then the rate of diffusion of unknown gas, which is denoted by R, X is equal to 1, and the rate of diffusion of gas hydrogen, which is given, it is 4. As we know the molar mass of the hydrogen, MH2, it is 2 gram per mole. We have to calculate the molar mass of unknown gas that can be write as mx, and we have to calculate this. So this is the required data. We will apply the simple relationship of Graham's law, which was rate of diffusion of hydrogen divided by the rate of diffusion of unknown gas is equal to the square root of molar mass of unknown gas divided by the square root of molar mass of the hydrogen. So here we have rate of diffusion of hydrogen is 4 divided by rate of diffusion of gas that is unknown, it is 1, and the molar mass of unknown gas can be written as mx, and the molar mass of hydrogen we have 2. So by rearranging all this data we gain m2 divided by 2 is equal to 16 by 1. So how we just calculate? By taking square on both sides. So all these squares just cut out, and 4 4 are 16. Next step is m2 is equal to 16 multiplied by 2, and the molar mass of unknown gas is 32 gram per mole, and the gas we have, it is oxygen gas, which is denoted by O2. As its molar mass is 16 multiplied by 2, we gain 32 gram per mole. So the rate of diffusion of hydrogen gas is greater as compared to the rate of diffusion of the gas oxygen. So this is the result that we just gained from this. I hope you guys understand about this topic, and the next topic we will discuss about the applications of the Dalton's law of partial pressure. What are the main applications, or where we can apply this Dalton's law of partial pressure of gases? For that time, you guys have a good day, and Allah Hafiz.